Greetings of the day, dear students. In this video, we are going to discuss about Norton's theorem. By the time we complete this video, we will discuss about its statement, equivalent circuit, and also an example, right? And one more example also we will discuss in this video, right? Most of the times you are going to do this experiment in your laboratory also, right? And if any this theorem states that if any linear two terminal circuit is there, it can be replaced by an equivalent circuit consisting of a current source in parallel with resistor Rn, right, where In is the short circuit current through the terminals and Rn is the input or equivalent resistance at the terminals. And while doing that, we have to make independent sources are to be made inactive, right? Then how do you understand this statement? Making source inactive in the sense, for example, in your in your problem, if any voltage source is given, simply short circuit that. If there is any voltage source, what you have to do, we have to short circuit that. If there is any current source, you have to open circuit that. If you have already watched the Thevenin's theorem, right, while finding the equivalent Thevenin's resistance, we have done that. Here, while finding the current, where the theorem is to be applied across those terminals, the short circuit current is to be found out, right? Now that equivalent current, Norton's current, will be in parallel with the or Nortons. Will be in parallel with the or Nortons. For example, sometimes you can do like this also. After finding its Thevenin's equivalent circuit, uh, if nothing is specified, right? You can find out the Thevenin's equivalent circuit, and at last we can find out the I Nortons, right? And R Nortons will be equals to the R Thevenins. Then how do we get the R I Nortons or ISA short circuit current? Simply after finding the Thevenin's equivalent circuit, right? By short circuiting these terminals A and B, the current flowing through this terminal will be our nothing but our I Nortons or ISC. I Nortons or ISC. So obviously now this current I Nortons or ISC will be equal to VTH by RTH. VTH by RTH. Like this also we can do, right? So what I want to say is uh, the circuit can be replaced with an equivalent current source in parallel with a resistor. Now let me do an example and find out the Norton's equivalent circuit. For example, this problem is given. We are supposed to apply the Norton's equivalent across A and B, right? So this is a voltage source. In this diagram, we are having a voltage source of 12 volts and a current source of 5 amps, R1 2, R2 3 ohms and R3 as 4 amps. Our first step will be calculating the Norton's equivalent resistance. How do we do that? We have to make the sources inactive. In this problem, there is a one voltage source. Simply short circuit that. We have short circuited the voltage source. And there is a 5 amps current source. Simply open circuit that. Right? Now looking into the circuit, we can observe that, for example, if current is flowing entering through this path, observe R2, R1 and R4. Current flows like this. R1, as this is open circuited, no current flows through this path, and after R2 it enters into the R1 and again it flows to the R4. Same current flows in R2, R1 and R4. Now these three are in series. R2, R1 and R4 are in series. Now the resultant is in parallel with R3. So that is what we have done here. So the way you look the circuit is important. Dear students, observe R2, R1 and R4 are in series. That is what we have done here. R2 plus R1 plus R4 in parallel with R3. Now 3 plus 2 plus 5 parallel with 4. 4 parallel to 10. If two resistors are in parallel, what we are doing, if RK and RB are in parallel, R equivalent, what we are saying, RA into RB, RA into RB by RA plus RB, RA plus RB. So that is what we have done here. Is 4 into 10 divided by 4 plus 10. We are getting 2.857 ohms. This is the way of finding the equivalent resistance. Equivalent resistance, right? Now, next step is the calculating the short circuit current. Across which terminals the theorem is to be applied, that terminals or those terminals are to be short circuited. In the given problem, he told us to find the Thevenin's equivalent across Norton's equivalent across AB. That is the reason A and B terminals are short circuited. Dear students, observe now in the given problem. Now once you have short circuited A and B in this question, A and B are short circuited like this. Now whatever current comes up to here will flow through the short circuit path. Now this a resistor parallel to the short circuited path can be removed. That is the reason why I tell number of times in circuits, the way we look the circuit is important. The way we look the circuit is important, right? Now this R3 is parallel to this short circuited path, right? Now we can remove this R3. Whatever current comes under and comes up to here, because of this is the minimum resistance path, entire current flows through A to B. No current will flow through the R3. So that is the reason why in this problem, while finding this current, I Nortons or ISC, now this resistor is removed. We have not drawn this resistor across AB. Clear? Right. Now our target is to find out this I Nortons. We can apply some simple mesh analysis to find out this. Two meshes are there. Two meshes are there. For mesh 1, let me take the current I1. Mesh 2, current I2. Now the voltage values, let you assign some polarities, some positive, negative, and some positive, negative. Right? From mesh 1, we can say that this I1 and 5 amps both are in the same direction. This I1 is flowing like this. In clockwise direction we have taken. Now this I1 and 5 amps both are in same direction. So indirectly I1 is equal to the 5 amps. I1 is equal to 5 amps. No need to apply KVL for this mesh, because one variable we got it, 5 amps we got it. I1 is all now solved. Now let me apply KVL to the mesh 2. Let me start from the voltage source. We will consider the current leaving terminal polarity throughout this course. Current leaving terminal polarity is considered for voltage sign. For voltage, whether you have to take plus V or minus V, it will be decided based on the at which terminal the current is leaving. In this problem, I2 is leaving the voltage source at positive terminal. I2 is leaving the 12 volts voltage source at positive terminal. So that is the reason we have taken 12 plus 12, right? Now come to R1. The resistor R1 is like this. I2 is flowing like this. This is the mesh current. I2 is the mesh current. Now I1 is flowing like this in R1. But we want branch current. What is the branch current? In the direction some positive to negative. Now the branch current will be equal to branch current. Now it is equal to I2 minus I1. So if somebody asks what is the voltage drop across R1, V equal to IR, we are very much familiar. We are asked drop across R1. Resistor value is R1, no doubt. But which current we have to take? Here the student gets the doubt. Here the student commits the mistake. The value of current must be branch current. Now in this problem, the current flowing in the branch is I2 minus I1. Whereas I1 and I2 are the mesh currents. To calculate the voltage drop, please take the branch current, right? That is the reason why I have voltage across R1. I2 minus I1 into R1. Which sign we have taken? Negative sign. Why? Because I2 is leaving the resistor R1 at negative terminal, right? Now we came up to here. Now I2 came up to here. What will be the drop across R2? Simply I2 into R2. What is the sign? Current is leaving at the negative terminal. Minus I2 into R2. Slowly we came up to here. Now the current flowing in R4 is I2. It is leaving at the negative terminal. So minus I2 R4 equal to 0. If this step goes wrong, entire problem goes wrong. This step is very important. If this step is correct, to some extent you can manage. If the first step itself went wrong, then the entire problem will go wrong. So please be very cautious while writing the KVL for a given loop. The key point is, for the given resistor, if you want voltage drop, please consider the branch current, right? This R2, in R2, mesh current is same as branch current. In R4 also, mesh current is same as branch current, but that is not the case with R1. With respect to R1, the branch current is I2 minus I1. Clear? Right. Now, once already we know I1, if we simplify this one, in the place of R1, substitute 2, R2 equal to 3, R4 is 5, 22 minus 10 I2 equal to 0, right? I2 equal to 22 by 10. Now, I2 is nothing but 2.2 amps, 2.2 amps. Clear? So, I2 is nothing but what here? This I2 is flowing like this only, I2 is flowing like this. I2 and IN, I Nortons or ISC, both all are in same direction. So our ISC equal to I Nortons is nothing but equal to I2, is nothing but equal to I2, right? Yeah. Now we have completed finding the Norton's current and Norton's equivalent resistance. What the statement says, the entire circuit can be replaced by a current source in parallel with a resistor, right? Now this Rn 2.857 will be in parallel with IN. What is IN? 2.2 amps in parallel with 2.857. This is the equivalent circuit. Clear? Right. So this is how we can apply the Norton's theorem. And if you want, we can apply source transformation for this one. And a current source in parallel with a resistor can be replaced by a voltage source in series with a resistor, right? Now that voltage source value will be how much? V equal to I into IN into RN. 6.2854 volts in series with 2.857 ohms. If of course this is not asked for you, this Thevenin's equivalent is not asked in the problem. Just we are supposed to calculate the Norton's equivalent, right? Next, let me see one more example, dear students. Now he's asked us to calculate the Norton's equivalent, Norton's theorem. Find the current through RL. Find the current through RL. Right? Now, in this problem, 12 volts voltage source is there. R1, R2, R3 are there. R1 10 ohms, R2 20, R3 is 30 ohms. Now RL equal to 100 ohms. Our target is to apply Norton's theorem across A and B. We have to apply Norton's equivalent. We have to find out Norton's equivalent across A and B. Clear? Dear student, if you observe one difference, in the previous problem, there is no element across AB. Already the element is removed. Across this AB, he has asked us to calculate the Norton's equivalent. But now in this problem, we are having an element across AB, right? Now we want to remove that element across AB, whatever element is there, we have to remove this element and find out the Norton's equivalent first, and later we can add that RL to the equivalent circuit. That is important. Clear? We are asked to apply Thevenin's theorem across Norton's theorem across AB. We have to remove this element. We have to remove this element and find out the Norton's equivalent. Clear? Now our first step is to find out the Norton's equivalent resistance. Our rule is make the sources inactive. If it is voltage source, we are making it short circuit. If it is current source, we have to make it open circuit and redraw the circuit. Looking into the circuit, we will find the Norton's equivalent resistance. In the given problem, there is only one voltage source that is short circuited here, and the element across A and B is removed. Now looking into the circuit, we have to look into the circuit, right? Now for example, if some current is passing or applied through this terminal, current comes up to here, right? Now current gets divided into I1 and R1 and R3. Now both the currents will meet again at this point. If you observe, R1 and R3 are in parallel. R1 and R3 are in parallel. That is what we have written here. In series with R2, right? Now Norton's equivalent will be R1 into R3 by R1 plus R3. Why? Because what is the formula? If two resistors are in parallel, 1 by R equivalent equal to 1 by R1 plus 1 by R2. If you take out LCM, R1 R2, the R2 plus R1, this is nothing but 1 by R equivalent. Now what will be R equivalent? R equivalent is nothing but R1 into R2. This is from the basic, R1 into R2 by R1 plus R2. If two resistors are in parallel, this is how we will find out the R equivalent. That is what we have done here. R1 parallel to R3. So R1 into R3 by R1 plus R3 plus R2, because this parallel combination is again in series with R2 plus R2. So 10 into 30 by 10 plus 30 plus 20. We will get 27.5 ohms. 27.5 ohms. Now this is our Norton's equivalent resistance. This is our Norton's equivalent resistance. What is our next step? To calculate the short circuit current or Norton's current across where? Across AB, right? That is the reason A and B, that resistor is removed. Now this AB is short circuited. Our target is to calculate current through AB. Let me apply the mesh analysis, right? Mesh 1 current I1 we have taken, mesh 2 I2, mesh 2 current is taken as I2. Let me apply KVL now, and of course you can assign some variables with some small uh, in small letters. Drop across R1 is V1, drop across R2 V2, drop across R3 is V3. Clear? Now KVL for mesh, we are considering the current leaving terminal polarity, current leaving terminal polarity for voltage, current leaving terminal polarity for voltage. We will start with the voltage source. Now this I1 enter here, it is leaving 12 volts at positive, so plus 12. Now I1 came up to here, I1 is leaving R1 at a negative terminal. So minus, what is the drop? Current flowing is I1 into R1. Clear. Now the question arises, here we are having R3, but we want branch current. Number of times I am repeating this point. To find out the voltage, for example, for this one, if I ask voltage V3 equal to I into R3, but which current we have to take? This is important. For example, I1 is flowing like this. This is I1, but mesh current. I2 is flowing like this. I2 is flowing like this in R3. Now, what will be the current, branch current? That current will be nothing but in the direction I1 minus I2. Very, very important. If here, this is the point where more chances to commit the mistake, right? Now, what is the branch current, dear student? Across through R3 is I1 minus I2 into R3. That is the reason I have taken. Now our drop across R3 is nothing but I1 minus I2 into R3. Now this current is leaving at the negative terminal. So that is the reason we have taken here minus. Clear? This step must not should be correct, accurate. Right? I repeat again, 12 minus I1 R1 minus current flowing, branch current in R3 is I1 minus I2 into R3 equal to 0. Clear? Right. For R1, branch current and mesh current both are same. Why? Because R1 belongs to only mesh 1. But observe, R2 is common to both the mesh 1 and mesh 2. In mesh 1, R3 is there. If you see mesh 2, in mesh 2 also R3 is there. So indirectly it is common to both the meshes I1 and mesh 1 and mesh 2. So in that case the branch current will not be same as mesh current. Observe R2. R2 belongs to only mesh 2. So branch current and mesh current will be same in R2, right? Yeah. Now uh, we will substitute the values of R1 and R3, right? 12 minus 10 I1 minus 30 I1 plus 30 I2 equal to 0. So that implies 40 I1 minus 30 I2 equal to 12. This is the first equation. Clear? Now let me apply KVL to mesh 2. KVL to mesh 2. In mesh 2, observe, dear students, there is no voltage source, but we can apply, not a problem. Drop across, for example, this is positive, negative. We have taken arbitrary signs. For R3 already you have assigned positive, negative, and the drop is V3, right? I2 flows like this. I2 flows like this. And this I2, this current is leaving at the resultant current is leaving at the positive terminal. So plus V3 plus V3. Now this I2 came up to here. This I2 is leaving R2 at negative terminal. So minus V2 equal to 0. Again, dear student, this step also must not go wrong. Very simple. Just simply consider this basic. Don't forget. Current leaving terminal polarity. Just simply check whether the current is leaving that element at positive terminal or negative terminal. Clear? Yeah. Now V3 minus V2 equal to 0. Now we are familiar. What is V3? V3 is how much? I1 minus I2 into R3. V3. In the direction of I1 we have taken positive. If positive is at the bottom, we might have taken I2 minus I1. Right? Yeah. I1 minus I2 into R3. This is V3 value. Minus drop across R2. Current flowing is I2 into resistor value, because we know the basic V equal to IR, V equal to I into R, right? So I2 into R2 equal to 0. Now on simplification, we will get 30 I1 minus 50 I2 equal to 0. 30 I1 minus 50 I2 equal to 0. Now two equations we are having. What are the coefficients of the first equation? I1 coefficient is 40. That is what we have written here, 40. I2 coefficient is minus 30, minus 30. Now from second equation, I1 coefficient is 30 plus 30. I2 coefficient minus 50, that is what we have written here, right? I1 into I1 I2 equal to 12, 0. This is in the form of A, X equal to B. Now X will be how much, dear student? X equal to A inverse into B. This is a 2 by 2 matrix in the form of A, B, C, D, right? Or you can do like this also. What will be the value of I1? 2 by 2 matrix solving. I1 will be delta 1 by delta. How we will get delta 1? I think but delta 1 by delta. I2 is delta 2 by delta, right? Now what is delta determinant? Determinant of 40 minus 30, 30 minus 50. So 40 into minus 50 minus 30 into this one. 40 into, right? 40 into minus 50 minus 30 into. So we will get delta value as minus 1100. Delta 1. While finding delta 1, just remove this 40 and 30. The first column is to be removed. This is first column, this is second column. And replace it with 12 and 0 here. Replace it with B matrix. B matrix. This is A, X equal to B. 12, 0. So now for that we have to find the delta 1. Similarly, while finding delta 2, in the delta matrix, we will remove the second column. In the second column place, now we will write 12 and 0. Observe. In the second column place, we will write 12 and 0, right? Now delta 1 is minus 600. Delta 2 is minus 360. So I1 value, I1 is delta 1 by delta minus 600 by minus 1100, 0.5454 amps. Similarly, dear student, I2 equal to how much? Delta 2 by delta minus 360 by minus 1100, 0.3272. Now, if you observe the diagram, our Norton's current, this Norton's current is nothing but ISC is nothing but our I2, mesh current I2. This I2 is flowing like this. I2 is flowing like this. This I2 and I Norton's both are in the same direction. So I2 equal to I Norton's equal to ISC equal to nothing but our I2. So we have completed finding the Norton's equivalent resistance and Norton's equivalent current, short circuit current, 0.3272 and 27.5. Now the theorem is we are asked to apply across AB, A and B. Now whatever the element we have removed across AB, that one we will join here. Simple. We have joined RL here now. Now we want to calculate this current. Out of this 0.372 amps entering here, what will be the current flowing through RL? This is just like two resistors are in parallel. If you remember the current division rule, right? If some current I, total current I is entering like this, if there are two resistors in parallel, R1 and R2, and the current flowing in is R1 is I1, current flowing in R2 is I2. Now what does the current division rule say? I1 equal to total current into opposite resistance. What is the opposite resistance? R1 key for R1, what is opposite resistance? R2 divided by total resistance. What is total resistance? R1 plus R2. Similarly, if we want I2, the formula is same, total current into, to calculate I2, opposite resistance. What is opposite resistance? R1. R1 divided by, what is total resistance? R1 plus R2. Similarly, here also now I want IL equal to total current IN into opposite resistance. What is opposite to RL? RN is there. RN divided by Rn plus RL. So for this circuit, by applying the current division rule, now IL equal to IN into, just in the place of um, uh, IN or I short circuit current, I Nortons, we have to substitute that value 0.3272 into Norton's 27.5 divided by 27.5 plus 100. So this is the current. IL is how much, dear student? 0.07057. If I write it in milliamps, it is simply 70.57 milliamps. So by applying Norton's theorem, we have calculated the current flowing through the resistor RL. Its value is 70.57 milliamps. 70.57 milliamps. Clear? What is the total input current here? 327.2 milliamps. 327.2 milliamps is entering. Out of that, here through RL, nearly 70.57 milliamps is flowing. Like that, we have to understand. If you want to calculate I1, this entering current minus this leaving current, we will get the value of I1 also, current through R Nortons. Clear? So, dear students, please remember in this entire discussions, whatever might be the given circuit, from the given circuit, you can replace it with an Norton's equivalent circuit, right? Um, a current source in parallel with a resistor. That current source value is nothing but the current across the short circuited terminals, and resistance is nothing but the resistance across those open circuited terminals, and by making the sources inactive. If it is voltage source, simply short circuit that, current source open circuit that. And I repeat again, don't think that for final answer itself only we will get the full marks. The moment you see the problem and if you are asked to apply the theorem, don't get afraid. Minimum steps we can write, no doubt. Confidently we can present some minimum steps by remembering the simple basics. First, redraw the circuit. This circuit, everybody knows the statement maximum. They can easily write that. It can be replaced by a current source in parallel with a resistor, up to there, no doubt. Now, finding the resistance, simply if there is a voltage source short circuit, current source open circuit, redraw the circuit. Look into the circuit. On looking that, you will get some idea which resistors are in series, which resistors are in parallel. Half of your problem will get completed by just simply calculating the equivalent resistance. This step easily we can do that. After that, across which you are asked to apply the theorem, just remove that element and short circuit that and calculate the current through that wire. Just you can apply in this problem, for me convenient to apply the mesh analysis. You can apply the nodal analysis also, not a problem. But our target is to find out the current flowing through I2. He will not specify you to apply which analysis. Be cautious while writing the KVL, Kirchhoff's voltage law. Basic fundamental current leaving terminal polarity. At which terminal the current is leaving, write that polarity for the voltage. While calculating the voltage drop, you have to consider the branch current. Right? If you are familiar with these things, easily you can solve the problems. Clear? Right. Thank you.